All right. Low turnout today. Let me see if I can get that chat open. Otherwise, I usually can't see the chat, but it's just us. So here we go. Hopefully I don't start typing stuff with my hand on the screen. All right. So in terms of review, maybe I'll close the door here just a second. Okay. It's weird because usually when I just teach online, you can see me, but now you won't know if I'm here or not. Anyways. And is it still just us? It is. Okay. Just checking. All right. So in terms of review, right, we went through, we talked about interpreting regression coefficients. I feel like I'm writing crazy big here. Right, and we said for multiple regression, well, we're pretty familiar with simple regression, right? Simple linear regression, the slope and the intercept, that's fine. But then for multiple regression, right, we have to remember that the coefficients, we can only interpret them assuming that the other coefficients are held steady, right? And so, so we started talking about that, and then we said, okay, once we built a model, right, we need ways to decide or to compare models rather. And so we need ways to assess and compare models we've built. Okay. So the first one that we talked about was the, and I always get them mixed up, the root mean squared error. And I'll do that here. The root mean squared error. And we did talk about it, but I'll jot it down here so you can see the similarities. Okay. It's the sum from I equals 1 to n of yi minus y hat, or yi hat squared divided by n. Okay. And then we said, okay, an alternative to this, now we want to minimize the root mean squared error, right? Because this is the residual and our goal will be to minimize the residual. Okay. So just so my screen isn't so cramped, if you are trying to put something in the chat, just unmute yourself, okay? Because I can't see it. So I'm gonna just, wait. Sorry. Now I know what's going on. It's when I close the screen, it actually closes the Zoom. Share my screen. I will not do that again. Sorry. Keeps recording though, I guess. It's weird. Yeah, looks like. All right. So like I said, if you have a comment, then just unmute yourself. I'll be startled because I don't know where it'll come from, but that's okay. So we want to minimize the root mean squared error because that would mean minimizing the residuals, which is a goal of ours, right? So want to minimize RMSE. We also talked about the RSE, which I always get confused because it's not the root squared error. That's what I want to call it, but it's the residual standard error. And it was very, very similar to the RMSE, except now we're going to penalize a model with too many predictors by taking the sum from I equals 1 to n of those residuals, yi minus yi hat squared divided by n minus p minus 1. Yeah. This n minus p minus 1, we said, okay, this penalizes you for having too many predictors in your model. Okay. It penalizes a model with too many predictors or with many predictors. Okay, but we still want to minimize it. How do we use knowing whether we want to minimize or maximize something? Well, if I'm choosing between two models and I've calculated the RSE, for example, then I would pick the one with the lower RSE. Now, that's from last day. A metric that we are used to using is R squared, right? So that's another thing that we could use to compare models. Okay. So another metric we could use is R squared. Okay. Oh, that doesn't look very nice. R squared, not much better. Oh well. Remember from Stat 230, R squared is the percentage of variability in Y explained by the least squares regression line on X or multiple X's. Okay. So R squared is the percentage of variability in Y explained by the least squares regression line on X, just generally, right? Or Xi's. You want to be more general about it. R squared, you could have the formula for it, or it's the correlation squared. Okay. But you want to maximize. We want to maximize R squared, right? We want to maximize the percentage of variability in Y. So how much of the activity in Y have we captured by this line on the explanatory variable? So default R output does not give you R squared, it gives you an adjusted R squared, and that's totally fine. It's very similar to the residual standard error versus the root mean squared error in that it's going to penalize you for having too many predictors. Okay. And so R output includes the adjusted R squared, okay, which is R squared, but penalized for including many predictors. But penalized for including too many predictors. So again, R squared and R squared adjusted, because they're similar, right? We still want to maximize R squared adjusted. Okay. Another kind of common metric is the AIC, Akeiki's information criteria. And it also relies on the number of predictors. Okay. So another metric we can consider is the AIC, which is, and I can never remember how to spell Akeiki's information criterion. So the AIC is going to be 2 times P, which is the number of predictors again, plus N times the log. Now, in statistics, we use the natural log, but we write log RSS over N. Now, this isn't something that you're going to calculate, but it's good to know where it's coming from. So that's why I'm not too picky about the log. But P is, again, the number of predictors. And the RSS is the residual sum of squares. Which is what? That's going to be the residual sum of squares. Off the top of my head, I'm pretty sure is just the sum from I equals 1 to n of yi minus yi hat squared. Residual sum of squares. I'll have to double check that, but I guess I feel pretty confident. If it's 2 times the number of predictors, right, and then I've got n, my sample size n times some log, right, what do I want to do? Well, I want to minimize my AIC. That's not obvious, but I also am being penalized by the number of predictors. So I know the higher the predictors are, the higher my AIC is, which is bad. So we want to minimize AIC. There are many, many other metrics, and depending on what field you go into, what you're going to find is you're going to get a job, and then you're going to find that, okay, at this workplace, they like to use the AIC, or here they like to use R squared, or you'll kind of pick up on what you should be using. Just be aware of all these model assessment techniques. Okay, so there are other metrics. Such as the Bayesian information criterion. Oops, that doesn't say criterion. which is abbreviated BIC. There's Mallows CP. Oops. And others. Right, there's lots and lots. I'm just going to check to make sure I'm not. Oh, 3 people here now. Wow. No one here in class still. That's okay. So what we've been finding, right, is we're constantly being penalized for having too many predictors in our models, right? And the reason for that is because if we're modeling, right, we don't just want a really good model for our sample, right? We want to have a kind of flexible model that can be applied to any new sample, right? Or ideally the population, right? And so if we kind of fine tune this model too much on our sample, which means incorporating too many predictors, right, or we overfit the model, then we're kind of exposing ourselves to having a model that can't be applied to a new sample or the population. So most of these metrics penalize a model with many predictors. That is because we always want to pick the simplest model, right? And so even though it looks fancy to have all these crazy models, really what we should be doing is we should be favoring the simpler model. So that is because we always want to pick the simplest model possible. Yeah. There's kind of 2 reasons for that, especially if you are presenting your findings, right? You would want to pick that easier model or the simplest model that achieves approximately the same amount of predictions, right? Or the same predictions, because it's easier to interpret and explain. Easier to interpret / explain, right? If it's your job to explain this model to the client and you've incorporated so many predictors, then you're going to have to explain all those, and that sounds terrible. The other reason is because it's reproducible, meaning it can be applied to a new sample, right? And be kind of flexible on that new sample or even the population. So it can be applied to a different sample and still perform relatively well. Okay. So we can compare overall models, right? But how do we decide on what predictors to include, right? So we can compare overall models, or we can also compare just the individual predictors inside each model. We can compare overall models using the metrics discussed. right? RMSE, RSC, R squared, AIC, etc. Yeah. But we can also compare individual predictors inside each model. But we can also compare individual predictors inside each model. So each coefficient is going to come from some sampling distribution or from a sampling distribution, right? And so we could use resampling methods to generate these estimates, right? Or I think the output in R is still using the established sampling distributions, which means we're going to have a standard error. But in our model, okay, we have estimates of each coefficient. We have estimates of each coefficient. Which we denote by BI hat. Each estimate has a sampling distribution. So it also has some standard error. So it will also have a standard error. The standard error of BI hat. So what I want to do is I want to run a multiple regression model in R and then look at the output. So I had it here, but it went to sleep, of course. Oh, system is overloaded. Of course it is. Whenever I try. Let's see here. Come on. So I'm just going to be using the code from the textbook. I thought it was going to be so quick and easy. Come on. Oof. Hopefully if someone's watching the video, they fast forwarded through this. It's painful. I guess I could have paused the recording. But I never think of it until it's too late. Come on. At what point do I give up? Let me see if I can find it in the textbook then. Sorry, it doesn't look like that's going to be giving me anything. Do I have any bookmarks here? Notes? No, not really. Well, it's simple regression, multiple linear regression. Okay. Mhm, mhm, mhm. I wanted the summary here. Fine. I'm gonna check to see if, oh, that's the wrong one. No, it's still going. All right, that's fine. I really just wanted to go through and generate this with you guys, but that's okay. Okay. So there's a house linear model, and the linear model is the adjusted sales price. I think it's adjusted sale price regressed on the square foot total living, the square foot lot, the bathrooms, the bedrooms, the building grade. Okay. And any uh, empty values or missing values are deleted. It gives us information for the residuals, which helps us check a few things, right? We can check, oh, I thought it gave us the mean. Anyways, we have to assess the residuals, right? To check our model. But before we can do that, let's just look at some of these coefficients. Okay, so here's some default multiple linear regression output in R. Okay, so we've got these the coefficients. Okay, we've got, this is the estimate, which we can replace essentially with BI hat, right? That's the estimate of the coefficient for each of these things. This is from the sample, right? And so, so that's why it's an estimate. We get the standard error, oops, the standard error of BI hat. If I have an estimate and I have the standard error, and I know it follows a t-distribution, right, with some degrees of freedom, right? We don't need to know it because they've already calculated t, right? But this t here is going to be BI hat divided by the standard error of BI hat. Okay. And then the probability of being greater than the absolute value of t, this is the two-sided p-value, right? And so this here is the p-value. Okay. Now, we can use these p-values, right? And so that's really what we're here for, is to be able to use these p-values to select the predictors that contribute significantly to the model. Okay. And so here, we use these p-values to determine which predictors contribute significantly to the model. Contribute significantly to the model. Okay. So what that means is if the p-value is small enough, so less than 0.05, although we've got these significance codes here, and pretty much all of them except for one have 3 stars, which means it's, you know, approximately 0 because it's so small, right? But so we can use these p-values to decide which predictors are worth keeping in the model. So the only one that's kind of jumping out as not significant, right, is the square foot of the lot. Okay. So in this case, right, what we would do is we would, and I remember technically we should move this predictor to the end of the list. right? Just to see, so the square foot law, just rewrite it at the end of the list. I'm not going to make you do that, but technically, I guess that's what we should be doing, or at least that's what they made me do when I was learning. Okay. And if it's still insignificant at the very end of the list, then we can remove it. Okay. It's possible you don't have to do that anymore, but I don't know, things change. So here, what we would do is we would remove this, the square foot lot. Maybe I'll use red. So this is not contributing to the model. So it can be removed. As you're removing predictors, you want to make sure that you're removing them one by one. Okay, and the reason for that is as you remove each predictor, right, how we define these coefficients, right, or how we interpret these coefficients is, okay, the square foot. So for each increase in total living square footage, right, then the adjusted sale price is going to increase by 2.288 times 10 to the power of 2, right, which is what, 2,200, I think, dollars. Okay. And so, but that's assuming that all these other things stay the same, right? And so if we remove one of these, then of course the coefficients are all going to change, as well as the p-values, right? And so here, if we remove a predictor or multiple predictors, or want to remove multiple predictors, we need to remove them one by one, right? To see how these p-values change, right? To see how these p-values change. We need to remove them one by one, right? Least significant first, obviously. To see how the coefficients and their p-values change, but really just the p-values, how the p-values change. Okay. It could be the case that the square foot lot, right, it's insignificant, but we keep it in there because all these other ones are significant, right? If we remove it, then maybe it was the glue kind of holding things together, right? Maybe there's some confounding variable with the square footage of the lot, right? Where it explicitly doesn't matter to the model, right? To the sales price, but kind of in the background, it might be. Okay. Let's see if this still resuming, huh? Let's see if I can. Okay. It is saying the system's overloaded, so I'll let it think about it, but I'm not going to rely on it. Otherwise, I was going to see what happens if we remove the square footage of the lot, right? What would happen to these p-values? So these estimates, right? These estimates come from the sample, right? And so then we use these estimates with the standard errors and we apply them to the population, and then we can kind of generalize to the population. But there's a problem, right? If we're using just our sample information to build this model and we have no way to check it, right? That could lead us down a bad path. So what we do is we assess our model using cross-validation. So we need to remember that our model was built using our sample. Right. And so to properly assess our model, right, how flexible is it when I apply it to a new sample, right? How well does it do when I apply it to a new sample? So to properly assess our model, we should use cross-validation. Maybe I'll use, right? And by assessing our model, what I really mean is how well does our model perform on new data? Right? That's what we're trying to find out. So cross-validation, first thing you're going to do is you split your sample into a holdout set and a training set. Okay. And your training set will be larger than your holdout. Okay. So cross-validation. Let's see if I can fit it on the same page here. Let's see. Cross-validation. First thing I'm going to do is I'm going to split the sample into a holdout set and training set. So you randomly divvy up the sample into a holdout set and a training set. And the training set will be larger than the holdout. Will be larger than the holdout. Okay, guess I couldn't fit it all on one page. That's okay. So now I've got this holdout set kind of on the ready, right, on just off to the side. And so what I'm going to do is I'm going to use this training set to build my model. Build the model on the training set. Or sometimes we say train the model. Now this really means build a ton of different models and pick the best one, or maybe the best 2 or 3, right? So really what this means is build many models, build many, many different models. And select the top performers. Could be plural. Usually you have 2 or 3 that you want to kind of send into the fighting ring. And then, right, you choose the ones with, let's use R squared because that's something we're comfortable with, right? So you choose the models that give you the highest R squareds, for example, but then you're going to apply it to the holdout set. Apply the model to the holdout set. um, to see how well it performs. Okay. It or they, right? And then select the model that performs the best on this new data, right? That was our goal, being able to model our new data that it hasn't been built on, or built using rather. And then select the model that performed the best. As your final model. You're usually only allowed one model in the end. Right? Sometimes we even do this, right? We do this many, many, many times, right? So each time you're going to have a different holdout set and a different training set, right? And then what can we do? Well, if we have all these different assessments, right? So if we're thinking about R squared, well, then for each one we could do, we could take the average R squared, for example. Right, so ideally, we do this many times. And with computers, we can. And we consider the average of the model assessments. And consider the average of the model assessment. Right, whatever it is, RMSE, RSE, R squared, etc. Right, whatever it is that you're looking at. So one of the ways, and kind of the most common way that we can do this many times, like I said, if we're trying to do this many times, there are techniques we can use. We can use k-fold cross-validation. K-fold cross-validation, which does what I was explaining. Okay. You're going to split your sample into k subsets, right? So instead of just a holdout sample and a training sample, now you're going to have k subsets. And at each iteration, you're going to use a different one of those subsets, one of those k subsets as the holdout set. Okay, so you're going to split the sample into k subsets, and then at each iteration, use a different subset as the holdout set. Okay. Good. Make this clear. Just gonna make sure I haven't missed anything. Great. It's hard because I can't see my Zoom, which I'm used to, but not in here. Okay, so we know how to assess our model, right? A couple of different ways. And then how do we pick the best model, right? You're going to use some version of cross validation, probably K-fold cross validation. Oh, that's what I wanted to check. It's still thinking. Oh boy. Okay, great. Right. And so now how do we build models, right? We could just there are a couple of different options, right? And so how do we decide which predictors to put into our model, right? So we now know how to assess our model. But we haven't looked at kind of the nitty gritty of how we build models. We just said, oh, here's a model and here's how we assess the predictors. Okay, and so maybe I'll add that here. We now know how to assess our model and our predictors. But we haven't looked at how we build models. Haven't looked at how we build models. Okay. So if you have a data set, right, then I was really relying on Studio Cloud to work for me, but that's okay. So if you have a data set, right, then you could have a huge number of predictors, right, or features or explanatory variables, however you want to call them, right, that could be included in your model. So how do we kind of sift through these to find what should be included in our model? So in a data set, we will have a number of predictors. Predictors or features or explanatory variables that could be included in our model. Included in our model. Sometimes we'll kind of have some background understanding of what's reasonable to include in our model, and that's great. But we can't rely on that, right? We're going to be bouncing around between different fields, and so we can't be kind of experts or kind of in our field in every single field, right? What we're experts at is building models. It doesn't matter what the data is. I'll start this on a fresh page here, but there are many ways to decide which predictors should be in our model. Okay, and so I'll talk about kind of the key ones here, but there are many ways to decide which predictors should be in our model. Okay. Option 0, and you'll see why it's option 0, is you could consider all possible subsets, right? So given if you only have 3 predictors to choose from, right, A, B, C, then you could look at just A, just B, just C, A and B, A and C, B and C, right? A, B, C, right? So all possible subsets, but you can can kind of see how that would spiral out of control really quickly if you have some even 5 predictors, right? Then you're considering all these all possible subsets. So for example, if there are 3 predictors, A, B, C, then you could look at y on A, y on B, y on C, y on A plus B, y on A plus C, y on B plus C. This isn't even taking into account interaction terms, or finally y on A and B and C. Okay. This is, of course, computationally expensive. So we don't tend to do that. Unless we have, a very reasonable number of predictors, then of course, look at all these different models and pick the best one. That's great. Then you can feel confident in your decision, in your model. The number 1 that we could consider, okay, is forward selection. Okay, now forward selection starts with just the intercept as your model. Okay, so no predictors. So forward selection you start with the intercept as your model, which means no predictors. Then incrementally add predictors. Incrementally add predictors. And there are ways, of course, to decide which ones to add. You could look at the ones that have the highest correlation with Y, right? You could put those in first, because they should help you model Y, of course. So don't worry, R kind of does it in the background, but then incrementally add predictors until they're no longer contributing. I guess, significantly to the model. Okay, so that's one way. The other way is kind of the opposite. It's called backward elimination, where we throw all the predictors in and then slowly pick away the ones that are least significant. And for me, that's the one that makes the most sense, right? Because then I don't need to figure out which one to incrementally add each time, right? Oops. Backward elimination. You start with all possible predictors in the model. With all possible predictors in the model, then incrementally remove the least significant predictor. Then incrementally remove the least significant, right? And that's what I was talking about before with those p-values. The least significant predictor which really means the predictor with the highest p-value. Okay. Until all predictors are significant. Until all predictors are significant. So I'll mention it here again, right? Just as a note, the p-values as you remove predictors, right? Those p-values, they're all going to change. Okay? So the p-values will change depending on what predictors are in the model. Depending on what predictors are in the model. Okay. And I guess I feel like I said it, but I do have a note in my notes, right? Significant. So a significant we use it generically to mean statistically significant. Statistically significant. Which means the p-value is less than the alpha level. Right. You're essentially doing a hypothesis test for each of those coefficients, but we don't go through the motions. A third option is a combination of the two. So the third option is stepwise regression. It's going to start with forward selection. So it's going to start with a constant model, it's called, when we don't have any predictors. Okay. And then you're going to incrementally add predictors, and then you're going to remove any non-significant predictors as they kind of come up, right? Remember, so those p-values are going to change as you add and remove predictors. Yeah. So you're going to start with a constant model. Right, which is from forward selection. So you start with forward selection, and a constant model is no predictors. That's a constant model. Right, it's just y is just y always. And then you're going to incrementally add predictors. So far that's just forward selection, right? And then you're going to remove any non-significant predictors. And remove any non-significant predictors, which is backward elimination. As they appear. Oops. Hey. I'm just teaching online, so you're welcome to listen, but yeah. um, someone's here, but no one from our class. It's fine. So of course, for all of these, um, I guess, model selection techniques, we use R, right? So use R to implement these model selection techniques. Okay. I think that's probably a good place to stop. Let me just check my notes here. Yeah. All right. Yeah, let me just flip through here. Yes. All right. So if you have any questions, let me know. Otherwise, I'll either see you or not see you on Thursday. Stop this.